Hey everyone, welcome. Today we're going to explore exactly how Python handles external data, and really why it's the absolute backbone of modern computing. If you've ever wondered how those massive databases actually feed into the apps we use every single day, well, it all starts right here. In this explainer, we're going to build a clear, step-by-step understanding of the entire data pipeline. Let's kick things off by looking at a huge problem in machine learning. You've probably heard the phrase garbage in, garbage out. In the ML world, models, like natural language processors or translation tools, learn directly from text data. But here's the harsh reality. If we feed our models messy, unparsed text files packed with extra spaces and weird special characters, our high-performance machines become completely useless. They literally learn the wrong things. So to avoid that nightmare, we absolutely have to provide pristine, pre-processed data. So here is the roadmap for how we'll build out our data pipeline today. First up, the data input problem. Second, opening and checking files. Third, reading the data stream. Fourth, cleaning messy strings. And finally, writing to text files. Let's get right into it. Part 1, the data input problem. This is all about the fundamental challenge of just getting data into Python in the first place. You know, early on in programming, we rely a ton on manual input, literally typing things in one by one. But when your programs scale up and you're dealing with massive amounts of inputs and outputs, that's just not going to cut it. Instead, we have to rely on plain text files, things like TXT, CSV, or JSON formats. Think of these plain text files as simple, incredibly efficient external databases that our programs can read from and write to continuously, even when the computer is completely turned off. Part 2. Opening and checking files. The crucial point here is figuring out how we safely access this data without completely breaking our program. In Python, your absolute best friend for this is the open function. It's essentially our gateway. Now, when you write this command, you have to give it two specific parameters for it to actually work. First, you need the exact file name and its extension, like datafile.txt. And second, which is just as important, you have to tell Python the specific mode you want to use to interact with that file. We've got 4 specific file opening modes at our disposal, and each one serves a very unique purpose in the pipeline. We use R when we just want to read existing content. We use X when we need to create a brand new file from scratch. W is for writing new data, but beware, this completely overwrites any existing content. And finally, A is for appending, which lets us safely tack on new data to the very end of a file. Oh, and one quick note. If you try to use R on a file that doesn't actually exist, your program is going to crash with a runtime error. No one wants that. Because of that exact risk, before you even try to open a file to read it, you've always got to do a quick safety check. By importing Python's built-in OS library, you can use the os.path.exists function. You literally just pass in your target file name, and it hands back a simple true or false Boolean value. True means you're good to open it. False means your program knows to stop or flag the user, which totally prevents a sudden frustrating crash. Part 3, reading the data stream. Okay, so the file is safely open, but how do we actually navigate these text files? What's super fascinating here is that Python looks at text files completely differently than you or I do. We look at a document and see formatted pages, nice paragraphs, distinct lines. Python, it just sees a continuous, endless stream of sequential characters. And crucially, this stream is packed with hidden special characters that control formatting, stuff you'd never actually see in a standard text editor. For instance, at the end of every single line, there's a hidden line feed character, which is represented by \n, and at the very end of the whole document, there's a hidden end of file, or EOF, character. So, if it's all just one massive stream, how does Python keep track of where it is? Well, the system generates this clever little hidden pointer. The second a document is opened, that pointer drops in at the very first character. Then, as your program reads through the document, the hidden pointer physically moves along the stream, character by character, perfectly keeping your place in the file. Let's break down exactly how the readline function uses this to push through a document. When you call readline, it starts grabbing text exactly where that pointer currently sits. It captures every single character it passes until, boom, it hits one of those hidden line feed characters we talked about. At that exact moment, it stops capturing, jumps the pointer over to the very first character of the next line, and just waits. The next time you call readline, it does it all over again. Eventually, it's going to hit that end of file character. When it does, it stops completely and hands back an empty string, basically telling your program, hey, we've reached the very end of the data. Part 4, cleaning messy strings. All right, we've extracted the data. Now we actually need to process it to fix that whole garbage in, garbage out problem. Our very first tool for this is the find function. I like to think of this one as our scout. We use it to pinpoint exactly where a specific piece of data is hiding inside a larger string. You just hand it a target string to look for, and it spits out the exact numerical index position of its first occurrence. And if the target isn't in there at all, it politely hands back a -1. This is so incredibly useful for checking if certain keywords or symbols actually exist in a line of data before we try to process it. Next up is the split function. Real-world data usually comes in these super long continuous strings, like in a CSV file where an entire row is just one giant block of text. Split lets us chop that string up into nice, organized list items based on a specific delimiter. By default, it splits whenever it sees a blank space, but you can easily tell it to split at a comma, a semicolon, a hashtag, whatever you need. This is a game changer because it instantly transforms a messy raw string into a highly structured Python list that's super easy to loop through. Finally, we've got replace, which is undoubtedly our Wayne weapon for swapping out bad data or just nuking unwanted characters entirely. If you're dealing with weird formatting glitches, or let's say you want to strip out all those hidden line feed characters, you just tell the replace function what the bad substring is and what the new correct substring should be. Now pay close attention to this because it's a super common trap. It is really easy to assume that replace goes in and directly changes your original string in memory. But actually it doesn't. It leaves your original string completely untouched. Instead, it generates a brand new string for you with all those replacements perfectly made. If you forget to assign that new string to a variable, your beautifully clean data just vanishes into the void, and you're stuck working with the same old messy data. So we've carefully pulled our data from a file, navigated all those hidden characters, and cleaned it up beautifully. But that brings us to a pretty massive question. All this clean data only exists temporarily in the computer's active memory right now. If the power goes out, it is gone forever. What good is this pristine, perfect data if we can't actually save it back out into the real world? Part 5. Writing to text files. Let's solve that final hurdle by saving our clean data for good. Remember those file modes we looked at earlier? By opening a file with the W mode for write and using the write function, we can blast our cleaned string directly into a new document. But seriously, a quick word of caution. The W mode is highly destructive. If you open an existing file in W mode, it will instantly wipe out every single thing that was previously in that file before writing your new stuff. It's totally perfect for generating fresh output files, but it is super dangerous if you're pointing it at an existing database. Now, if we want to protect our old data, like if we just want to add a new user's record to the bottom of an existing employee database, we use the A mode. A is for append. This is brilliant because it safely opens the file, takes that hidden pointer we talked about, moves it all the way down to the very end of the existing data, and only writes your new information right there, safe and found. And that brings us to the absolute most crucial final step of this whole process, using the close function when you're completely done reading or writing. This ensures your new data is properly flushed and saved to the hard drive, and it frees up your system resources. If you leave a file hanging open, your memory gets tied up, and way more importantly, your new data might not actually get saved properly, which is a massive risk for data corruption. Always, always close your files. Which brings us right back full circle. As the source material puts it, by mastering the handling of text files, we can create valuable and high-performance machines. If you can lock down these simple data pipeline steps, checking, opening, reading, cleaning, writing, and closing, you literally hold the keys to feeding and training the most powerful machine learning models on the planet. So the question is, what massive data set are you going to build a pipeline for first? And more importantly, once you've truly mastered plain text files, how are you going to handle millions of real-time data streams?